portions which we have studied last time. Yes, we have done last time. Last time we were discussing about the forms of potential energy. We discussed about the potential energy and its form. Now, forms of potential energy. There were two forms which we have studied: gravitational potential energy and your elastic potential energy. And I hope all of you remember what is elastic potential energy. Anybody can write down in the chat what is elastic potential energy. Which we try to define as the potential energy possessed by the body due to the position of the body. This could also be defined, or this was also been defined as the energy possessed by the body due to the force of attraction, of the body unit. Today we will start with the gravitational potential energy at the height h. Okay. So if we have to find out the gravitational potential energy at a certain height, then how we are going to do it and what it will be. So we are going to do the derivation of the gravitational potential energy. It's just, if we define it, it's the, if we are trying to find out the gravitational potential energy at a certain height above the Earth's surface, then it is the amount of work done in lifting up from ground to that height. Now suppose if I have a body and this surface we consider it as a ground. Now this body, if I try to take it to a certain height h, alright, then the work is to be done against the force of gravity. Okay, let the mass of this body be m. So we are trying to lift this body, so the force is applied, so work done in this case is equal to force applied into the displacement. This is your standard formula which we are taking. Now force applied here will be your m into g, whereas the displacement will be the height to which it is being taken. And therefore we find that the work done against the force of gravity, that is stored in the body in the form of potential energy, which we call it also as gravitational potential energy. Now gravitational potential energy Ug can be called as this work done, which is equal to mgh. So gravitational potential energy for a body at a height h is given by Ug is equal to mgh. Few things you can note it down from here, whatever you are in your rough final notes I will be sending. thrown up, okay, or a body falls down. Now suppose if a body is being thrown up from a height h1 and reaches to h2, okay, having a mass m. So the potential energy at a height h1, this will be your mgh1, whereas the potential energy at height h2 will be your mgh2. So increase in potential energy this will be given by mg h2 minus h1. This will give you the increase in the potential energy. Why increase? Because as the displacement increases, so it has to do more work. We already know that displacement is directly proportional to the work done, and therefore from h1 to h2 we find that the height from the ground is going to increase, and therefore the potential energy is going to increase. Similarly, in case if the body is being dropped down from h1 to a height h2, is that your h1 is greater than h2. So here u1 will be equal to mgh1 and u2 will be equal to mgh2. This will cause the decrease in potential energy, which will be your u1 minus u2, that is mgh1 minus h2. So when a body is being thrown down, we will observe that there will be decrease in the potential energy. If the body is thrown up, so as it gains the height, there is increase in the potential energy. Now in general, we find that potential energy, that is gravitational potential energy at ground is considered to be 0. So this is a standard. Otherwise, what happens? Say, if I consider here ug as 0, ug as 0, so the value above this, let me draw it clearly. So if I consider this position as A and say the ball is being thrown up from this position and this position as B, such that UA is considered as 0, then UB will be equal to mgh, which means that the work done is going to be positive and your potential energy is also positive. U is positive over here. But now if I consider the same case, but there is a slight difference. I consider position B as the point of reference, okay, and we consider that UB is equal to 0, then UA will be equal to minus mgh. Okay, the reason is that here we find that the work done is going to be against, this is the zero considered, and if you consider the number line, the value below zero will be considered as negative, and therefore we consider that the work done here will be negative. This is also an answer to the last time I had asked a question that at infinity the work done is considered to be, the potential energy is zero due to the force of attraction. But at certain finite distance, it has been considered that the gravitational potential energy is negative. So, in the same respect, here also if you observe, it depends. Many of you have given the correct answer, all those who have given me the answer. And so here also point has to be taken care that what reference we are taking as. Okay, where is the reference point? Reference point means where we are considering the zero potential energy. So if we are considering the Earth as a zero potential energy, above Earth it will be positive, below Earth it will be negative. Somebody said that yes, if we take, say for example, if we are throwing a ball into the well, then the work done will, or rather the potential energy will consider to be as negative. Is gravitational potential energy zero at certain height, then above that height it will be positive, below that height it will be negative. So that is how we have the concept of positive and negative potential energy. Keep in mind, potential energy is a scalar quantity. Positive and negative is just indicating the work done, and therefore and in particular about work done also, if you see, it's not exactly telling me the direction, it's telling me that whether the force applied is and displacement is in the same direction or in the opposite direction. Okay, so I hope up till here it is clear. If you have any problem, you can ask it in chat. Work done by the body, Mayank, you had asked, work done against the gravity is negative, so how can UV be positive? Okay, see, it's a reference point if we are considering the reference, that is zero potential difference, potential energy at the ground is zero, then above zero is considered as positive. Also you will see, as per the definition, it is the work done against the gravity. So when we are applying a force and we are trying to move the body from A position to B position, okay, so that is how the work done becomes positive. Now, I had just taken a case where we are considering that instead of ground at zero potential energy, this is just as consideration, okay. If we consider that UV is your point where the gravitational potential energy becomes zero. Okay. So that is an assumption which we are considering, that if we consider the point to be at point B the potential energy is zero, then what will be the nature of potential energy below and above? So that is why we have, it's not exactly that it is a negative. Okay, these are the two different conditions we are considering and in which we are having this. So standard way, we will consider that ground is zero, and then we will consider the potential energy. I hope this is clear to all of you. One more question I get into mind. Somebody asked me that a stone is having a potential energy, positive or negative. Now keep in mind, if the stone, as I told you, that ground is considered to be negative, therefore we find, therefore we find that if you are keeping therefore we find that if you are keeping the stone on the ground, it will have zero potential energy. If you take the stone to a certain height, then it will have some potential energy. So the stone itself, you have to specify whether it is on the ground or it is at certain height. So now we come to the next topic, that is kinetic energy. We have already studied about potential energy. Now, kinetic energy is also defined as, if you wish to write down, you can write down, but I'll be giving you the notes. So, kinetic energy has been defined in a simple term. It has been defined as the energy possessed by the body due to it's a state of motion. That is, if a body is in motion, the energy which it possesses is called as your kinetic energy. For example, if I take a stone and throw it, so when it is moving, okay, during that motion, it will be having a kinetic energy. A car is in motion, a bicycle is in motion, okay. If you see the moving hands of the clock, that is the needles of the clock, they are having the kinetic energy, and especially the second hand, okay, because that is continuously moving, so that will have the kinetic energy. This is one way of defining the kinetic energy. The other way is in terms of your work done, because energy is basically the measure of work or vice versa. So just like we have defined it in terms of the potential energy, here also we define it as the amount of work which a moving body can do before it comes to rest. So how to find out this kinetic energy? When I say that it has got a certain kinetic energy, when I say that it has got certain kinetic energy, so in terms of work done, how it can. See, for example, if I consider a stone coming towards me. Now, if I have to stop it, so I have to apply a force. Okay. And then the force which I have to apply will cause some work to be done. Now, this force is going to do the work which has been required to stop it, say for example. So the amount of work which is done, that will be equivalent to the amount of energy that a stone is going to have. And that is why we can say that the kinetic energy can be measured, or kinetic energy is measured in terms of the amount of work done by the moving body before coming to rest. Now what does it mean? Let me explain you through a small derivation, okay, to show you the expression for the kinetic energy. So what we consider a body okay, this has got a mass m, alright. Now this is already in motion. So suppose this is been moving in this direction, okay. So let the motion, let the direction of motion be this. So we'll consider a body of mass m moving with the velocity v, okay, in the direction, okay. Now what we do, we have to find out the kinetic energy present in this body. So what we do, we apply a force which is trying to oppose it, or which is trying to bring it to rest. So once we apply a force, say we apply a constant force over here, and it makes the body to move a distance s before it comes to stop. That means the velocity here becomes your 0. Okay, but before coming to stop, it covers a distance s. Now, if it is stopping, it is going to retard and let the retardation be a. Alright, although a acceleration represents a, here we are representing the retardation. Let the retardation be a. So once again, I just give you an intro to what we are doing. We are considering a body moving of mass m, moving with a velocity v in a particular direction, and we apply a constant force to stop this body, and this body retards uniformly with a retardation a, and finally comes to rest, and before it comes to rest, it covers a distance s. Now we will be using this information to derive the kinetic energy. So here, so now what we find, we try to calculate the retarding force. So we calculate the retarding force F over here. This will be equal to M into A. The standard formula. Let this equation be 1. Okay. Now the kinetic energy which we will be calculating, or which we have to calculate, the kinetic energy which we are going to calculate, that will be equal to the work done by this retarding force before it stops covering a distance s, and therefore this will be equal to work done, which will be equal to F into s. Let this be the second equation. Now what we have to do, F we are doing, because we are already using the word retarding, therefore the retardation is not been mentioned as minus a, we are using it as a, and therefore F equal to ma gives us the retarding force. Now suppose if I am not using this term retardation, then I'll be using minus a, and which will indicate that it is a retardation. Overall the same. Now to find out s, now what we have to do, we have to find out f we are knowing, we have to find out s. So to find s, we use the equation of motion, but before that we have initial velocity, because the body is already moving. Initial velocity, which is represented by u, is equal to v. Here we are taking v as an initial velocity from the standard point of view, although u can also be taken, or you can take any variable. So here we are using it v, because in your book also the reference is taken as v. Final velocity, I hope all of you know it, how much it will be. You refer to the diagram. Final velocity was 0 because the body was coming to rest. Similarly, retardation we are already knowing. Retardation is equal to a, or if you want to express it in terms of acceleration, then we can represent it as minus. Now the equation which we are going to use, we have v, we have u, we have a. So, and we have to find out s. So the relationship is your third equation of motion. V square is equal to u square plus 2as. So if we put the values, final velocity 0, initial velocity v, so it becomes v square. Now retardation, I am using the acceleration, so it becomes your minus 2as. So s from here will be your v square upon 2a. So now what we have, This we mark it as third equation. So we have S is equal to V square by 2A. F from the first one we are having F is equal to MA. So now we are going to put in the third equation, that is this equation. So I'll just clear it. So now we have, if we substitute the values of F and S in equation 2, so equation 2 was K, now I will write down it as K is equal to F into S. The value of F was M into A into the value of S was V square upon 2A. So from here we get A being cancelled out. As a result, we are left with half mv square. This is equal to K. So this gives us the expression or the mathematical relation between to find out the kinetic energy. In other words, we can say that kinetic energy is equal to half the product of mass and square of velocity. So I hope this derivation is clear to all of you. Now, so if we go for the standard ones, the symbol once again, symbol of kinetic energy, this is given by K, capital K. Unit, this will be the same as that of the energy. So SI unit, it will be joules, and CGS unit, it will be ergs. Erg. Erg. By nature, it will be a scalar quantity. Work, power, energy, all three of them are your scalar in nature. So whatever positive, negative we are considering, we are just considering the direction of the force and the displacement. Energy or work as a whole, we are just keeping it as a scalar quantity, because whenever we have to specify energy or work, we do not specify the direction. Now we come to the forms of kinetic energy. Just like we have the forms of potential energy, similarly we have the forms of kinetic energy also. Alright, so here we have now, as the kinetic energy is the energy possessed by the body due to the state of motion, therefore the forms of kinetic energy also depends upon the different type of motion the body may possess. Now, this chart is going to show us the three basic motions which are taking place. The three basic motions which are taking place, that is your translational motion, rotational motion, and your vibrational motion. Now we all know that translational motion is a motion along the straight path. So if any body which is moving along the straight path, possesses the kinetic energy. That energy is called as your translational kinetic energy. So translational motion will give rise to the translational kinetic energy. Similarly, rotational motion will give rise to the rotational kinetic energy, and vibrational motion will give rise to vibrational kinetic energy. So these are the three basic forms of the kinetic energy. Whatever kinetic energy they possess, in general, we will say them as your kinetic energy, unless until it is specifically been asked to mention which type of kinetic energy. So now if we go for the definition given for the translational kinetic energy, it says that the energy possessed by the body due to the motion in straight path is called as your translational kinetic energy. Okay. So if a car is moving along a straight path, then the energy which it will be possessing, that is called as your translational kinetic energy. Or a body which is freely falling down. So when it is freely falling down, it is under a translational motion. That is, it will fall straight along a straight path, and therefore it will have the translational kinetic energy. Or the motion of the monatomic gas. Monatomic means it will have a single atom, one atom. So that is not going to collide with the other. I'm talking at the atomic level, not the molecular level or the material or particle. Okay, so single atom when we are talking about its motion, so its motion will be in a straight line, and hence that will also is an example of translational kinetic energy. Then we have rotational kinetic energy. It is defined as the energy possessed by the body due to the rotation of the body about an axis. Very simple. If you spin a top, so the top will be spinning about its axis. Now, the energy, since it is spinning motion, so it will have a kinetic energy, but this motion is a rotational mode, therefore it will have a rotational kinetic energy. The earth rotating around on its own axis, that is the rotation of the earth. Okay, you make a ball to spin. Okay, so that will also a rotational kinetic. So wherever the rotational motion is going to occur, the energy possessed will be your rotational kinetic energy. Then we have vibrational kinetic energy. Then now vibrational kinetic energy is the energy which is possessed by the body which is having due to the vibration of the motion. Okay, we all know that. Say for example, what is a vibrational motion? Say if you take a string and plug it in between, the motion it will be performing, that will be your vibrational motion. Now, vibrational motion, so the energy which it will be possessing at that instance, that will be called as your vibrational kinetic energy. Okay, similarly, what when you might be doing, take a metal scale, place it on the edge of a table, hold it from one edge such that one end, such that the other end is free, and then you try to vibrate, you hear the sound also. Okay, now since the scale is vibrating, so the energy which it will be possessing, that is your vibrational kinetic energy. So these are the three types of vibrational, rotational, and translational kinetic energy. These are the different type of kinetic energy. Now keep in mind, although I have explained you separately, but at a time, a body may possess one or two or all three type of kinetic energy. A body is spinning also and going along a straight path also. Okay, so it may be having a rotational and your vibrational. Say for example, uh, so polyatomic atoms, polyatomic, monoatomic, tetratomic atoms. So if you have got more than one atom, so what will happen? These atom may be, we all know that these atom undergo a spinning motion also, they undergo the rotational motion also, they collide with each other, and for a certain part of the motion they might be in a linear motion also, and they will also be going about to and fro, or rather the vibrational motion. So a polyatomic atom, the motion, the kinetic energy possessed by the polyatomic atom is an example where it may be having the all the three type of kinetic energy, that is rotational, vibrational, as well as your translational. Okay, so there may be various instances, there may be various examples where we have such type of such type of examples where the body may be getting these different type of kinetic energy. Okay, so I hope up till here it is clear to all of you. If you have any question, yes, Ashutosh, you have asked, Ashutosh Ranjan, you have asked that the formula same for all type of, yes, kinetic energy. See, these, when we are specifying in particular the type of motion they are performing, then we say that okay, this is a vibrational, this is a rotational, this is a translational kinetic energy. Mathematically, to calculate kinetic energy, we always use K is equal to half mv square, so that will remain same. Can kinetic energy be zero? If the mass is zero or if the velocity is zero, then the kinetic energy can be zero. But ideally, if you say, because when we say that all the bodies are, at least if we go for the subatomic level, then they all are in motion. Okay. And also you may have studied about the concept of absolute zero. So it has been considered that at absolute zero, the motion of the particle ceases. So in that case, it will become zero. So practically, or you can say ideally, the particles or the body is, the kinetic energy cannot be said as zero. But yes, definitely, if I am taking a car and my car is standing, okay, it is at rest, then we'll say, okay, the body is having zero kinetic energy. So I hope that is not going to create a confusion. Yes, you can calculate the rotational and vibrational kinetic energy. In that case, you will have to find out the rotational, that is your angular velocity and other things. At this level, we are not going to study about that. You will be studying that in your higher classes. Okay, or if you have a question, or if you have a liking for that, then you can go for the class 11, where you can find out this. Okay. Yes, definitely. Mass cannot be zero. So basically, the kinetic energy is more or less depends upon the velocity only. Okay, and hence we can say that the kinetic energy is basically the factor of the velocity. Okay, because if we are considering a body, it will have a mass. Mass happens to be an integral property of the body, fundamental property of the body. In case, Kritin, you have asked why monoatomic atom has translational energy but polyatomic. See, in case of monoatomic, you just consider, say, for example, hydrogen. We consider that a hydrogen atom has got only one atom. Okay, I'm talking about atom. Now, in case of hydrogen atom as a whole, I'm not going to the subatomic particles in this case. You can consider that this is alone in the world. Now, if it is alone in the world, it does not get any collision or any other impact from some other particle. therefore, in that case, whatever path it will be following a straight path, and that is why we consider it as compared to your polyatomic atoms. We consider that it will be having only translational energy. Angular momentum basically is related to your circular, just like you have got the linear momentum, the same reference if you are considering for the circular motion, then we call it as an angular momentum. So circular motion is not in detail with us, so you can go through, there are various books or sources available where you can find out this angular momentum. But in particular, if you want, then I can provide you, I have to ask separately. So now I move to the next portion, an important part. And I find out of 300, why so less attendance? Your friends are not interested. So I'm keeping the attendance. Alright, so we move to the next topic. That is relationship between the kinetic energy and momentum. Just now somebody was asking the momentum. And I hope all of you know what is momentum. Okay, so momentum is basically been defined as the product of mass and velocity. So we will be trying to find out the relation between the kinetic energy and momentum, how they both are related. So here, what we do, we consider a body of mass m moving with velocity v. So let us consider a body of mass m moving with velocity v. Okay, so here if we try to calculate the kinetic energy, this will be equal to half mv square, and if I try to find out the momentum, then this will be equal to mv. Now, from this relation, that is from the relation of momentum, we can find out v is equal to p by m. Okay, now we'll substitute the value of v in place of velocity in kinetic energy. So k can be written as half m p by m whole square. Okay, so this we get it as 1 by 2 m into p square by m square. So this will be cancelling. So k can be written as 1 by 2 p square upon m. Or I'll rub that portion. Or from here we can get p square is equal to 2k. So either we write down p square is equal to 2k, or we can also write down p is equal to 2km, or p is equal to square root 2km. Alright, so this is the relation between the momentum. So either we can say that the momentum square of momentum is equal to twice the product of kinetic energy into mass, or we can say that momentum is equal to square root of twice the kinetic energy, the product of kinetic energy and mass. So this is the relation between the momentum and the kinetic energy. Now here we have two cases. Why we are studying? What is the use of this? Okay, what implication we can have? So the implication we are going to study, the significance we are going to study with two important case in this case. Okay. So what we are doing here is we are going to consider two cases. In case one, consider it as case one. I consider two bodies, body A and body B, such that mass of A we consider it as ma, let it be small n, and mass of B is considered to be as mb, which is equal to capital M, such that your small m is less than capital M, or in other words you can say that A is a light body and B is a heavy body. Okay. Now we consider that these two bodies move with the same momentum. Okay, the momentum of A is equal to momentum of B. Let it be same, let it be P, which means that they both are going to move with the same momentum. Okay, keep in mind, momentum should not be confused with the moment of force. Now, if I have to find out, now in this case what we are going to do is, we are going to find out, since momentum is constant, we have to find out the kinetic energy. So kinetic energy of A, if I try to find out, okay, so this will be reusing the relationship what we have studied just now. So kinetic energy will be equal to PA square upon 2m. Similarly, or we can write down as PA is equal to P, so P square upon 2m. Kinetic energy for V, this will be again PV square, this will MV, sorry, MA, mass of A. So mass of A is considered as M, so 2m, and this will be your PV square upon 2mb, and hence it comes out to be P square upon 2m, capital M. Now we have to find out since we have to compare them, so what we are going to do, we are going to find out the relation between them, that is Ka upon Kb. This will be P square upon 2m upon, so this will be 2m upon P square. So P square cancels, this 2 cancels, and finally we are going to be left with Ka upon Kb is equal to m upon small m. Now what does this signifies? This simply signifies that we have already studied before that m is greater than small m, which means that Ka will be greater than K, which means that a lighter body will have greater kinetic energy as compared to the heavy body. That is, kinetic energy of the lighter body, A was the lighter body, that is more than the kinetic energy of heavy body, B was considered to be as a heavy body. This I'll explain you. I'm also going to explain you using an example. Okay. So here again, we are considering an example. Let body A and body B. Let the mass of A be 10 kgs and mass of B be 5 kgs. That means this one is heavy and this one B is your lighter body. Alright? Let the moment be 100 kilogram meter per second, that is the unit, and PB is also 100 kg meter per second. So from here, if we try to find out the velocity, now we all know that P is equal to mv, implies that V will be equal to P upon m. So velocity for A will be equal to PA. PA is equal to 100 upon m, that is MA, 10. It comes out to be 10 meter per second. Similarly, for VB, this is again P is equal to 100 upon 5. It comes out to be 20 meter per second. Now I try to find out the kinetic energy. Ka will be half m, that is 10 into 10 square. V square, that is 10 square. It comes out to be your 500 joules. Whereas in this case, Kb, if you find, this is 1 by 2 into 5 into 20 square. And this value comes out to be 1000 joules. So what we find? Lighter body. So we find that lighter body, greater kinetic energy. Heavy body, less kinetic energy. And therefore, we can make out that in a simple term, it's a very simple to understand also. That means if momentum has to be same and the mass is different, then definitely their velocities will be different. Heavy body will be going by the lesser velocity and the lighter body will be going by the greater velocity. And as a result, we find that since the velocity is greater, so your kinetic energy becomes great. Okay, so kinetic energy for the lighter body will be more as compared to the kinetic energy of the heavy body. So I hope up till here it is clear to all of you. Basically, giving you the relation between the kinetic energy and your momentum. Yes, definitely M and V, we are already aware of the relationship, but A and P was not been calculated, so therefore we are trying to find out. If you replace that value, yes, definitely you will get the same thing. Okay, so I hope this is clear to all of you. This part, it's 4:59. according to my, so the class is going to be over. We are left with one more case in this, okay, and then we'll move to the work energy theorem. Meanwhile, you can go through the exercises. I'll upload the notes today in the group, and then you can note it down. I hope the previous work is all complete. Please, students, please be very serious. Okay, this is your 10th class, so don't take it very lightly. Keep on updating your work. I know that you might be getting the work in the different subjects also, but please continue doing it so that when the school reopens, you don't have the burden of the work to be done. Okay, so now it's going to be bye from now.